This video is going to be an overview of my playlist of videos on climate change. Obviously, a lot of these videos go into the same topics in a much greater detail. So first of all, carbon dioxide, the greenhouse effect, are these bad? Well, the first obvious statement that must be made is obviously no, because if you were to measure the temperature which we would expect our planet to have, and we'll consider Venus as well, just based on its distance from the sun, our planet should actually be much colder than it is. So if that was how we determine temperature, the farther you are from the sun, the colder you are. The Earth's overall temperature would be far below zero. There would be no liquid water on Earth. It's much warmer than that. Why? Well, because when energy from the sun reaches our planet, some of it is kept around the planet. It is trapped there because there are heat absorbing gases in our atmosphere. Venus has even more. So notice that Venus's temperature is 450 degrees Celsius as opposed to the 100 degrees, which would be predicted from its distance from the sun. So first off, the fact that there are heat trapping gases in the atmosphere and a greenhouse effect is not a bad thing. In fact, our planet depends on it. But obviously, if the amount of heat trapping gases were to change, well, then that would change, temperature, and there would be implications to that. Now, why would that be the case? Why would, I don't know, molecules trap heat? Well, we know that there's a spectrum of electromagnetic radiation. And so there are radio waves, there are X-rays, there's infrared, there are gamma rays, and then within visible light, there's blue, there's purple, there's green, etc. Now, molecules can absorb packets of energy, but which packets they absorb then correspond to where electrons sit in shells around the atom because they absorb only enough energy to jump to the next shell, etc. And so some molecules absorb different types of wavelengths. The sun's energy coming to us, there's a spectrum of different forms of energy, but notice a lot of it is in the form of visible light. The energy which leaves our planet is in the form of infrared radiation or heat. And if any molecules then have atoms structured in such a way that they will absorb wavelengths of infrared radiation, then they would block this heat from then being lost into space. Now, once again, each molecule would then have its own specific spectrum, and you can see that just by looking at the shirts your classmates wear, because some shirts are green, some shirts are blue, some shirts are black or white, and this means that the dyes in the shirt absorb and reflect different wavelengths of light. So a white shirt would reflect all types of light. A black shirt would absorb all types of light. That's why a black shirt is hotter in the summer than a white shirt. If a shirt looks blue to you, it's because the blue light isn't being absorbed. It bounces off that shirt to your eye while that shirt is absorbing other wavelengths of light. A green shirt would absorb red light and blue light, but reflect green. And so we're surrounded by molecules which absorb certain wavelengths of light and reflect others. And so heat is a form of radiation. So these individuals, if you have the right camera, you could see heat coming off of them. And there are molecules that instead of absorbing packets of blue light or red light absorb heat. Carbon dioxide, and this is frozen carbon dioxide becoming gaseous, and so carbon dioxide does absorb infrared radiation. And this is not in question. This can simply be measured. You can, pass infrared radiation of various microns, various wavelengths through a spectrophotometer, and then see if carbon dioxide will absorb some of it. And so that if you have a sample of carbon dioxide, less of it will pass. So clearly some gases um, are greenhouse gases which absorb heat. So which one is, which are the major ones? Well, water vapor is the number one greenhouse gas. And so water vapor will help absorb some of the heat that would otherwise be lost from the surface of our planet and go into space. One of the reasons for this is that as long as a molecule has more than two atoms, then it will absorb some heat. The bonds can bend relative to each other. The bonds can stretch relative to each other. So the fact that water is H2O, there's more than two atoms, it's not then a surprise that it absorbs some heat. That would actually be, expected. All molecules more than two atoms should absorb heat. And so when sunlight comes down to our planet, it warms it up, and then this heat will then go into space. But because there is water vapor in the atmosphere, then a lot of this heat does not go into space, but then rather is reflected back towards the surface of the Earth. So water vapor is a major heat trapping greenhouse gas. But just like shirts can absorb, reflect, blue light, but absorb green light, water vapor does not absorb every wavelength of infrared energy. Once again, it depends on where the electrons sit in their shells as far as how they can be absorbed. And so, I'm sorry, I don't know why we're paused. And so water vapor doesn't absorb every wavelength of light. So for example, infrared wavelengths in these microns, 5, 6, 7 microns, they can be absorbed by water. So water vapor can help retain energy of these wavelengths. But here you see what's called a window. Water molecules do not absorb infrared radiation in these wavelengths, say 9, 10, 11. And so infrared radiation of these wavelengths will escape into space. So these are known as infrared windows. So as we focus on other molecules which trap heat, the ones which are most significant are not the ones which absorb heat, say in this range or this range, because water already does, and there's a lot of water in the atmosphere. The question then is are there molecules which absorb some of the heat in these windows? So carbon dioxide will absorb radiation here and here where water will not. So the more carbon dioxide that there is in the atmosphere, the more heat which will be absorbed. Once again, carbon dioxide has more than 3 atoms, so there will be bond bending and bond stretching. So carbon dioxide is a heat trapping greenhouse gas. And more significantly, it does trap some of the heat that would otherwise escape through one of these windows that water vapor does not absorb. And so I repeat that in this next video. And carbon dioxide isn't alone. There are other gases which can absorb infrared radiation in those windows as well, like methane and nitrous oxide. So here, notice there's still heat escaping into space, but if you were then to add methane and nitrous oxide, you would see that they do absorb heat. They have more than 2 atoms, so that's expected, and you can measure that. Once again, you can see that less heat, less infrared radiation will pass through a column of methane or nitrous oxide. So this is not in question. And more importantly, they absorb heat within these windows that would otherwise escape into space. So methane is a heat trapping gas. Nitrous oxide is a heat trapping gas. Ozone is also a heat trapping gas. Now, one might argue that there's a whole lot of water in the atmosphere. There's a lesser amount, but certainly a significant amount of carbon dioxide. Methane's contribution is rather small. There isn't much methane in the atmosphere. And while that may be true, even though all molecules, all of these molecules are absorbing heat, they can absorb different amounts of heat. So for example, if we were to compare how much heat, say a kilogram of methane would absorb as opposed to carbon dioxide, 1 kilogram of methane absorbs as much heat as 34 kilograms of carbon dioxide. So even though there's more carbon dioxide here, the amount of heat that's absorbed is the same. So methane has a global warming potential of 34. Nitrous oxide has a global warming potential of 298. And then there are other molecules that might be produced, in say refrigerants or in chemical processes. You might once again say, oh, there's not much of them being released, but some of these have global warming potentials of 1,500, 15,000, 32,000. And so a small amount of these molecules has an enormous potential to warm the planet. And so carbon dioxide being the main one, I'd like to begin with that, but then we can touch on other ones as well. So carbon dioxide, and once again, this is dry ice, and the gaseous carbon dioxide is leaving from it. It is in the atmosphere. But because living things need carbon, our bodies are made of sugars, of proteins, of nucleic acids, of fats, then we rely on what we call producers, green plants, green algae, which perform photosynthesis. They take carbon dioxide out of the air, and using the energy of sunlight, they convert this into biomolecules. So the carbon cycle then begins with the producers, such as plants, which are creating biomolecules through photosynthesis. Well, plants can then get this energy out of the glucose molecules they've made. They perform respiration and produce carbon dioxide. Animals can eat the plants and then break things like sugar down for energy and release the carbon dioxide. Animals can eat each other. And then the carbon, which was trapped in biomolecules, then goes through the Krebs cycle in cellular respiration and then becomes carbon dioxide. And so this may come into your body as breakfast, but it leaves your nose in the form of carbon dioxide. So thus we have a carbon cycle. Not only do living things return carbon dioxide to the air through respiration, but when they die, then decomposition will then return the carbon of their bodies into carbon dioxide. And so there is a cycle where carbon is taken out of the air. It moves through food chains, and then either through respiration or through decomposition after death, it is returned to the air. As long as this carbon cycles, then the amount of carbon dioxide in the air shouldn't change. However, animals don't have to return their carbon to the atmosphere after they die. So if we were to consider, say, marine life of ages past, or plant life of ages past, while much of that carbon was returned to the atmosphere and cycled once again, some of it did not. So some of these were buried and they did not decompose, releasing carbon dioxide, and thus their carbon was trapped. And so, for example, in the Carboniferous period, about 350 million years ago, there were these vast coal forests where when wood and other material died, it then did not decompose, but it was trapped in swamp water and became muck that was ultimately compressed over time, and then ultimately formed these vast seams of coal. Coal can be used for energy, just like you could burn a modern living tree and heat your house. You could burn the remains of these ancient trees and provide the electricity that you just saw. When marine life is trapped and all that carbon is compressed, that can create petroleum. But so then the difference is, while this carbon, when we burn coal for electricity or burn petroleum to move our cars, this was not carbon which was already in the carbon cycle. It had been buried. It had been removed from the carbon cycle for millions of years, hundreds of millions of years. And so when we burn fossil fuels, this is carbon which had not been in the carbon cycle. We are now putting it back in, and therefore the amount of carbon dioxide in the atmosphere is increasing. That can easily be measured. Since the 1950s, there have been measurements on the amount of carbon dioxide in the air. Now, it goes up and down um, with the seasons. So for example, there are a lot of plants in the northern continents which drop their leaves, the leaves decompose. But apart from this, yearly cycle, because we are digging up coal to provide the electricity for this city, right? So, it is buried carbon, which is producing all of this light. It was buried petroleum, which was moving all of these cars. If we were to start in the late 1950s, one could see a steady increase in the amount of carbon dioxide in the air. So in the late 1950s, there was less than 300 parts. Michael, I think it was just over 300. I'm sorry. So just over 300 parts per million um, uh, carbon. So carbon dioxide, if you compared how much carbon dioxide there were for all of the other molecules in air, so once again, for every million particles, there would be about 300, slightly over than that. But ever since the 1950s, we have seen a steady increase to the point where now it's over 400. So about a quarter of the carbon dioxide in the air is new in my lifetime. I'm not that old, all right? But nevertheless, we have seen such a dramatic increase in the amount of fossil fuels for an ever-growing human population that the effects on carbon dioxide levels have been significant. So once again, carbon dioxide levels are certainly going up. This can be measured. There has been a steady increase because of human activity and the amount of fossil fuels that we use. Now, obviously, this is something that everyone on Earth contributes to, but not everyone contributes equally. And so if you were to compare per capita carbon dioxide increases and look at the average person in the world, how much carbon dioxide do they produce into the air, say in a year, versus in China and India, you can see that the United States is far outside the normal range, far greater than average. So while everyone on Earth is responsible for more carbon dioxide increasing in the air, in many countries, such as the United States, our use of cars, our use of electricity, the high amount of beef which we have in our diet, which requires a great amount of fossil fuels, means that the average American is contributing far more to the increase of carbon dioxide in the air than the average person on Earth. So this is a fact. The amount of heat trapping carbon dioxide is steadily increasing. One would then predict that if the amount of heat trapping gases are going up, then the temperature would be getting warmer. And that is easily seen. So if you were to take, I believe this is from as of 1970, and ask what were the hottest years on the planet, notice that as of 1970, the hottest years were 1944, 1938, 1953, some in the 60s, so a distribution of years. But if you were to then jump ahead in history and ask in 1980, there were still a lot of years, but notice there were a couple of 1970s years. If you were to ask the same question as of 1990, look at all of the 1980s years. So the 1980s were on balance so much hotter than everything that had come before. When you ask that same question in the year 2000, the 1990s were by far the hottest decade. There's nothing in the list that isn't the 1990s or the 1980s. If you were to then go to the year 2000, then most of the time, other than 1998, which was a much warmer than a normal year in the 1990s, are all recently. So clearly the temperatures are increasing, and one can measure that if one were to look at heat that way by measuring the hottest years. 2014 was the hottest year as of 2014 until 2015. And then 2015 was the hottest year on record. And then 2016. So as we'll see, not only did each of these 3 years break all known records prior, but that and never before had we recorded 3 consecutive years where each year then broke the record for the hottest year. Because this is such a huge concept, let's look at it another way. Let's imagine that this yellow bar, this horizontal bar, represents the average temperature of the world from the year 1900 to the year 2000. So all of the temperature measurements from every year, we get an average, and this yellow bar represents the average. And then you could ask, is any individual year colder than average, in which case we could have a blue line going down, or warmer than average, and then we have a red line going up. And as you can see, the 1900s began with years which were consistently colder than the 20th century average. For a while, it could be a little warmer, a little colder. This would be 1940, 1941, 1942. So it could be a little warmer, a little colder, a little warmer. So there could be some variation. But then notice that ever since the 1970s, so starting in 1977, every single year has been warmer than the average temperature from the year 1900 to the year 2000. And as I had said, not only is it warmer than average, but the temperatures have been going up. And then we have continued to set records year after year. And so there is a clear relationship here. The global temperature is increasing. There is no question about this. And I have a couple of versions of this because very often after another year passes, then we can say, oh, okay, so let's add one more bar to this this graph. So I have a couple of videos which say similar things, but very often we're made with one more record. So for example, the 3 record-breaking years, 2014, 15, and 16, that had never before been seen. So the amount of heat-trapping gas, thanks to human activity, is steadily increasing. The temperatures are steadily increasing. Neither of these are in question. What would be the consequences of steadily increasing temperatures? Well, a lot, and I'd like to just highlight a couple. First off, as temperatures get warmer, ice will melt. Now, ice, we certainly have become accustomed to it. There's a lot of ice in Antarctica, in Greenland, the Arctic, in glaciers. However, the reality is that our planet is currently much colder than it used to be. So in the age of dinosaurs, for example, there was no polar ice. So the planet just was warmer than average, and sea level was higher than average. So this ice does not have to be there. All right, once again, during most of the past 500 million years, there would not have been these glaciers and polar ice. So there can be more ice on Earth, there can be less ice on Earth. And what we are certainly noticing is that the amount of ice is decreasing. Now, this is Mount Rainier, the largest, which includes the largest glacier in the continental United States. And whether one looked at this glacier, which used to extend further, or any of the glaciers in the continental United States, they are receding. So if you look at where the glaciers extend, it is less and less with each year. Now, each glacier can itself have its own scenarios. So not all glaciers grow or recede at the same rate. So for example, that last glacier, there was kind of a landslide which covered part of it. And so the sediment which covered part of it prevented it from receding at the rate that neighboring glaciers were. That has stopped, and now it's receding once again. But just this is the average. Each glacier in different parts of the world can then experience different scenarios. But this is seen all over the world. So whether one were to look in the United States, in Europe, in Africa, in the Andes, one sees that glaciers just keep getting smaller and smaller. Ice is melting. What we know of as Glacier National Park may not have glaciers in it in the near future. Very often they melt, and then there are glacial lakes which then take their place. And so once again, this can easily be documented. There is ice which is breaking away from ice shelves. And so there was a huge ice sheet in the year 2002, which broke off of the Larsen B ice sheet of Antarctica. And so the county where I teach, there was a piece of ice that was 1.5 size the size of that county, which broke off. If we measure the ice in the Arctic, we have very good measurements where every year the ice will expand in winter, melt in summer. But if you were to pick a month, so for example September, for example, and you were to look at the sea ice area, it goes up, it goes down. But if you were to look, say, at 1980, where the ice measured 8 million square kilometers, and then just go year by year, and these are all maps where this ice sheet is mapped every single day. You can look at it for yourself. Notice that by the time we're getting to 1989, there are 7.1 million square kilometers. By the time we get to 1999, 6.3 million square kilometers in September. Now, there are yearly fluctuations, and every year can vary, but notice there is an overall trend that the amount of ice is getting less and less. And so if you were to pick certain years, you can actually have years where the amount of ice is half what it was in 1980. So these are millions of square kilometers, all right, millions of them that used to be ice no longer are. Now, one can observe this in the Arctic. Antarctica is a bit different because we have to consider both land and sea ice. But the reality is there is less ice now than there was a few decades ago. And this is a concern, not only because it is evidence that the Earth is warming, but then also this white ice is reflecting light. So light goes back up into space. Blue ocean absorbs light. And so therefore, the more of this ice that melts, the faster the oceans will warm, because the less light which is reflected into space. And so, depending on the month, you could say, compared to 1980, how much less ice is there? Very often it would cover, most of the continental United States, the ice that has been lost merely since 1980. Greenland has an enormous amount of ice, and the amount of ice in Greenland is steadily decreasing. So none of this is in question. The amount of heat trapping gases continue to rise. The temperatures continue to rise. The amount of ice continues uh, to melt. So here you can see if one were to measure the loss in Greenland, it would average to be about 269 gigatons per year. So this is an incredible amount of ice being lost from Greenland. So ice continues to melt. Where is this water going? Well, clearly into the oceans. Sea levels have risen in the past century, and they continue to rise. And clearly then this threatens coastal areas where when you look at Miami, there are certain times of the year with tides where much more of the seas intrude further, and the city is planning that certain areas may no longer be livable. New York City certainly has to pump water out every single day, which is accumulating under the city. Islands are threatened, and some islands actually are being abandoned because it is realized that soon they will not be livable. Venice certainly has ever rising ocean levels, and so as more and more ice melts, this is clearly going to affect the coast because more land will be covered by water. And since we have so many cities close to the coast, this will undoubtedly affect cities. It will affect ports and shipping lanes. But there are effects of climate change even if you don't live near the coasts. As our planet warms, this affects then the amount of severe weather. And so there will be severe storms with more severe precipitation, with more severe winds, which will become more frequent. Certainly, this is a concern given the damage that severe weather often um, often causes. And so if the same amount of rainfall falls in the area, but more of it falls at once, then this obviously increases flooding, and the frequency of floods and the severity of floods have um, have been rising as would be predicted in climate change. And then the frequency of severe storms, whether this be um, tornadoes or hurricanes, we have certainly seen an increase in the frequency, the severity, and then also just the enormous damage that that they can do. And so Hurricane Maria hit the island of Puerto Rico. It was a Category 5 hurricane shortly after shortly before hitting Puerto Rico, and did an incredible amount of damage. Now, the reality is when you have damage to a certain degree, which then say knocks out electricity, which prevents people from getting medicines and running water, etc., that this then causes an incredible amount of hardship. And so that it has been estimated that the death toll resulting from 3 million people losing their power was more than 5,000. I had the pleasure of visiting Puerto Rico a year after Hurricane Maria, and still there were plenty of houses where blue tarps covered their roofs. So even a year after the hurricane, the situation had not returned to normal. And that was one hurricane. And certainly, if we were to look in previous years. We could find many examples of other hurricanes which had done enormous damage, such as Katrina uh, and many others. Very often, when we look at a year and ask how many severe weather events have there been, which would then do damage, well, we can see that it very often breaks records. So if you were to measure how many disasters there are, natural disasters influenced by severe weather events. So sometimes these are snowstorms, sometimes hurricanes, sometimes floods, that we have ever increasing damage and human hardship, economic hardship due to severe weather events. There are so many other implications to this. The frequency of wildfires and drought are increasing, which affect our ability to raise crops. As temperatures rise, this will affect the disease organisms, right? Because very often it's cold winters, which will limit the number of, a parasitic population, or there are many species of mosquito that carry specific diseases which don't frequent North or at least the United States, because it tends to be colder. But as climate changes, then that can change, and we could see new disease organisms. Certainly, animals have adapted to a specific set of environmental conditions where they do well, and this would include temperature. But as the climate changes, this will then affect them as well, and some populations may dwindle. They may no longer be found in certain areas. They then may become endangered, such as the polar bear. So as Arctic ice decreases, then this is clearly threatening polar bears, which are now losing the areas that they have to hunt. Climate change has so many effects. So coral reefs, which I cover in greater detail elsewhere, are so incredibly important. About a quarter of all of the ocean's fish spend at least part of their life cycle in a coral reef. But corals are damaged by warming temperatures, by excess carbon dioxide, which then acidifies the oceans and makes it harder for them to make the calcium carbonate of the corallite that makes up the reef. And so this is going to have an enormous effect on wildlife as well. We'll see many species of wildlife moving farther north as far as their range goes. On mountains, we'll see that we'll start to see animals occurring at higher elevations than they once did, and those organisms which lived at the highest elevations, they may no longer be able to live there at all. And this then has so many effects. So for example, we are seeing increasing numbers of wildfires in the American West. And this is largely due to climate change, but many separate effects of climate change. So for example, there is less rainfall, so it is drier. It is hotter than it used to be, so that also is a contributing factor. But also because the winters aren't as cold, there are insects like the mountain pine beetle, which are not being killed off to the same extent. And so then comes summertime, the trees, which are already stressed because they need water, it's hotter and drier than it usually is, they now have more insect pests to these already weakened trees. This helps to kill the trees. And so now this adds to the wildfire risk. And so something like the frequency of wildfires, climate change increases this in many separate ways. And so climate change is a huge environmental factor. I have other videos which talk about, there's, the frost-free season is changing. As I can cover Elsewhere, certainly our diet affects this because, for example, getting your protein from um, beef is so much more carbon intensive. There's so much more fossil fuels needed to get protein from beef than from plants. I mentioned that in the fossil record recently, we think that the climate was shifted dramatically in times when a lot of melting fresh water then entered the North Atlantic, which then altered the currents, which helped to determine global climate, and thus the melting of the Arctic and Greenland we are concerned about because this might alter climate again. And so I go through a number of different effects of this, ranging from very warm years where in the Northeast United States where I lived, it's so warm that the ski slopes have to close because there's no snow in what should be the time of where they have the most skiing in February. Nuclear reactors sometimes have to shut down in summers because the water that they use to cool the reactors is just too hot because the temperatures are hotter than usual. And so this is one of the great environmental challenges that we face. As we put more and more heat trapping gases into the air, the climate will warm, ice will melt, and then this will cause oceans to rise. But in addition, there will be changes um, to wildlife. So for example, here I am kayaking in February, looking at bald eagles at on a lake which is typically frozen, that would not be able, to have bald eagles around it in February. And so this playlist tries to overview a host of, and this was that ski slope that I had mentioned. Climate change is going to affect humanity and other organisms in many, many ways, and is one of the most significant environmental issues that we face.